I guess.
Oh, yeah. Continue.
All right, let's get started. Thanks everyone for coming, either in person or virtually. It's glad to see the faces here. This is perhaps one of the first hybrid talks in the last like 18 months, 20 months at Waterloo. So it's cool to have this. And which better speaker to have here as one of the first hybrid speakers at Waterloo than Ayush Sekhari. Ayush Sekhari is he's a PhD student at Cornell, and he happened to be in town. And so he's done some really cool work in the sort of intersection of theory, the theory of machine learning. And today he's going to be telling us about SGD, the role of implicit regularization, batch size and multiple epochs, a very exciting area where I think we don't really quite know what's going on here, and hopefully Ayush will help illuminate it for us a little bit. Without further ado, take it away.
Great. Thank you, Gautam. So this is joint work with Satyan Kale and Karthik Sridharan. Before I start, I should say, like, please feel free to stop me if you have any questions. Like, I don't have a lot of slides. It would be good to make it interactive. So over the past decade, machine learning has led to many empirical breakthroughs in computer science, from solving complicated games to building the best computer vision softwares. In most of these applications, the state-of-the-art performance is achieved by using very large, complex, and over-parameterized learning models, typically where the number of trainable parameters is much larger than the number of available data points for training. And such complicated models are trained by formulating the learning problem as a high-dimensional stochastic optimization problem. To formalize, in stochastic optimization, one is given a set of models W and a loss function f that defines the loss of a model W on a data sample Z. There's some unknown distribution D over the instance space or data space Z, which induces a test loss defined as the expected loss when a new data sample is drawn from the underlying distribution. However, the learner does not know either the test loss or the data distribution, but has access to a data set S of n samples, which are drawn independently from the data distribution. And the goal is to find a epsilon suboptimal model for the unknown test loss F. That is the model W hat, for which the test loss is as good as the best model in the class, up to an epsilon error.
Right. So just to be clear, you're just talking about like the test loss, not necessarily over the training.
Yeah, so all I care about is performance over the test loss, which is the expected loss when new sample is drawn from the distribution.
What does it mean, capital Z there and S? Instance space and
yeah. So let me give an example and then I can answer that question. So consider the example of image classification where you want to classify cats and dogs, pictures of cats and dogs. So here the set of models could be neural networks. So W can denote the weights of a neural network and the loss can be cross entropy loss. There's an unknown distribution over the pair of pictures in the corresponding label. And the space of all possible pairs of pictures and corresponding labels is the data space Z here. The test loss is what we want to perform under. And a training data set is a collection of some pictures and dogs. Okay. Now, such high-dimensional stochastic optimization problems are hard in the worst case. In particular, in most of these practical applications, the loss surface induced by these models is non-convex. And it's well known that in neural networks used in practical applications, they have spurious local minima that are hard to escape. On the other hand, we also have computational hardness results, like explicitly showing that, for example, even learning a single layer neural network takes over polynomial time. Even if the best loss in the class is 0, it's still a hard problem. And there are a lot of works showing hardness of working with these models under various settings. However, deep learning has been a very successful revolution. We train these models every day. They work well in practice. And in fact, if you ask a practitioner, like at a bird's eye view, the approach that is generally taken is as follows. You collect a huge data set, construct a over-parameterized model class, typically a deep neural network. And then you train it using a local search method like SGD, Adam, and Adagrad. And what's observed is with a little bit of hyperparameter tuning, this three-step approach typically finds a well-performing model. Now, of course, in order to attain state-of-the-art model in various domains, you need to.
You have chat on? I think Jarvis might ask a question.
Oh, I do have chat. Let me see.
No, I have a question. I don't know how to chime in.
Yeah, sorry. We're just Ayush is turning on his sound so that you can ask. I don't think he can. I can turn on my headphones, but I can't. You don't think is your sound on?
Oh, actually, my sound is not on. Thank you. Yeah. Okay, now it's on. Sorry.
Do you want to try again, Shai?
Yeah. So already at this point, I want to point out. I mean, you were talking about computational complexity, but now you are talking about sample complexity. When we talk about over-parameterization, the problem is first the issue of generalization of sample complexity. Optimization is over the sample, but optimization doesn't give you guarantee of the behavior. So you talked about statistical guarantees, then you switch to computation complexity, and there are two different aspects, and I think they should be more explicitly distinguished.
Yeah, I agree. I will come back to distinguishing them explicitly. I agree with you, Shai. So in terms of like the hardness results that I just presented, most of the results that I presented are computational, but later on we'll also see some like statistical differences. Okay, so I'll proceed and maybe come back to your question later on. Okay, so this three-step approach typically works well in practice. And this leads to the question whether this big empirical success of deep learning can be boiled down to just using over-parameterized models with SGD. And in terms of over-parameterized model, the idea is like you construct a model where the number of parameters is much larger than training samples. Of course, the architecture needs to be like somewhat domain specific. You have different kinds of models for vision versus sound. But the algorithm is generally stochastic gradient descent that's used to train them. And it's a simple algorithm. It updates the current model by using the gradient of the of the loss function on a batch that is sampled from the data set that we have. Here, eta is the step size. So let me now discuss some empirical observations, and then we'll go more into theoretical details. So what has been observed in practice is that over-parameterized models trained using SGD work very well for a lot of these problems. Furthermore, the more you over-parameterize, the better performance you get. So in this experiment, they considered two layer neural networks where they increased the width of the network, and they observed that training wider and wider networks led to better performance. It has also been observed that taking multiple pass over the data set keeps on improving the performance. So in typical deep learning training setup, it involves taking like 100 passes over the data set. And what has been observed is that performance keeps on improving even when the training losses reach 0. Finally, it has also been observed that using a small batch size for SGD finds better solutions as compared to using a large batch size. So in this experiment, the small batch size corresponds to a batch size of 32 and the large batch size corresponds to a batch size of 10,000. And we can see a huge difference in terms of the performance of the final solution they return. So to summarize, like SGD works well in practice, small batch size SGD finds better solutions, and taking multiple passes over the dataset helps. So the main question we are interested in this work is why does multi-pass small batch size SGD work so well in practice for these high-dimensional stochastic optimization problems? So stochastic convex optimization is is one of the most well-studied stochastic optimization problem. So in this work, we start by looking at stochastic convex optimization as a case study. I'll first introduce what stochastic convex optimization setup is, and then discuss various aspects of SGD for SCO problems, and then conclude by discussing beyond SCO deep learning setting. Any questions so far? Okay. So in stochastic convex optimization problem, our goal is to minimize an unknown test loss using samples, where the test loss is a convex function in the parameter that we're optimizing. In addition to this, we also have some other structural assumptions like the test loss is Lipschitz, and the variance of the gradients is bounded. These assumptions typically hold in most of the applications where SCO problems arise. Yeah.
Can you repeat the question with the math?
Yeah. So Matt is asking if there's a constant in terms of definitions of Lipschitzness and variance. Yes, like whenever you have a Lipschitzness guarantee, you assume a constant over there. Just to simplify the presentation, I made them all one.
And just to distinguish this from the general case, maybe none of you hold in like neural networks, for example.
Sorry, can you repeat the question?
Like you're saying that none of these might hold in the neural network setting, for example. Can you repeat the question also so that the audience can hear?
So Gautam is asking if any of these assumptions hold in the neural network setting, and I'm not sure. Like I don't think neural networks are Lipschitz.
Sure.
Yeah, or even convex.
Yeah. I have another question here.
Mm-hmm.
I mean, what is the loss function that is convex here? I mean, we are usually interested in the probability. I mean, if you just classify images to dogs and cats, then we are usually interested in the 0-1 loss, which is not convex.
Right.
So the convex, using a convex loss instead of the loss you care about introduces another source of mismatch that maybe should also be taken into account.
Right. So far, I'm just considering the problems where only the test loss is convex, and I have no guarantees on the instance loss f of WZ. And this is an important distinction that will come into play later on. But again, like the reason I'm looking at SCO problems is to motivate an understanding of various aspects of SGD, which arises in solving like high-dimensional non-convex optimization problem. But at the same time, I also agree that maybe like jump from convex to non-convex is such that like we need new insights for non-convex, but we can come back to that.
Okay.
Yeah. So only the test loss is assumed to be convex. And in this setting, it is well known that SGD performs and succeeds to find a minimizer of the test loss. A classical result from Nemirovsky and Yudin in 1983 shows that if you run SGD using a single sample at a time, use all the samples that take one pass over the data set and use a step size of 1/√n, you end up finding a solution that is 1 by square root of n suboptimal. I'm of course hiding all the constant dependencies in terms of Lipschitzness and variance. And this matches the lower bound of, worst case lower bound of 1/√n for SCO problems. Okay, so this is a very important positive result that we need to keep.
I mean, again, this is, I think this is wrongly stated, because the result is about the sample error, not about the distribution error, because you don't take here any class or into account. The result, I think, is about approaching the minimum possible sample error, but not distribution error, because there is no generalization component here.
So the way Nemirovsky-Gradient stated the problem is I'm minimizing function f, where all I get is a stochastic gradient with bounded variance. And the guarantee is in terms of the minimization of f.
I see. Okay.
And once we try to interpret it for machine learning setting, this has like equivalence in terms of sample complexity being optimal, right? Is that your question?
Yeah.
But that's the interesting part of the Nemirovsky-Gradient analysis. The way they show this result is only for stochastic optimization of an unknown loss given stochastic gradients. Okay, let me quickly go over this proof of Nemirovsky-Gradient because it will help with some insights. So there are three technical parts in the proof that SGD works for SCO problems. The first observation is that the SGD update implies the following control over a linear term in terms of the gradient times the gap between WT and W star. The second technical insight is if I take expectation on both the sides, on the left-hand side, I can go from a sample loss to the test loss. And on the right-hand side, I get a bound on the variance and so on. And finally, for convex functions, the suboptimality of a function is upper bounded by this linear term, which is the product of gradients and the gap between WT and W star. So combining all these three together, we get a guarantee in terms of suboptimality of the return solution. And by plugging in the appropriate step size, you can get a 1/√n rate of convergence. Okay. Now, this is all for the convex case. In general, for explaining the success of SGD in practical problems, one popular theory is that of like implicit regularization or implicit bias. The belief is that for problems where SGD succeeds in finding a good solution, it has an implicit bias that drives it towards these good solutions. And this implicit bias is captured by the idea of regularization function. So the idea is for problems where SGD works, there exists some implicit regularization function RW, such that the solution that is returned by SGD is approximately equal to a minimizer of the empirical loss, regularized with this function RW. In fact, for many problems like matrix factorization or convolutional neural networks, etc., existence of this regularization function has been explicitly shown. And this might lead one to surmise that maybe this is a universal phenomenon in the sense whenever SGD works, there exists some regularization function that explains the success of SGD for that problem. And in particular, we know that SGD works for SCO problems, as I just discussed. We have a proof for that. So what is the problem-specific regularization function RW that explains the success of SGD for SCO? So we were trying to figure out what this regularization function was, and then in the end, showed a negative result. So in particular, we can show that for any regularization function R, there exists a SCO problem for which the point that is returned by the ERM algorithm with that regularization fails to be a good solution of the test loss. And in particular, this negative result holds even if you scale the regularization function in a data-dependent manner.
So I have another question.
Mm-hmm.
I mean, we have no free lunch theorems, right?
Right.
And they say that any algorithm, no matter what the algorithm is, there will be a problem for which it will fail. Right. So what's special about, if we already know that for every algorithm there will be a problem on which it will fail, what's special about showing it for a specific algorithm? It looks like it is implied by the general no free lunch theorem.
Yeah, so it is true that for any regularizer, there will exist some problem for which it fails. The interesting thing here is that that problem is an SCO problem. And it shows a gap between ability of SGD to, so SGD solves any SEO problem, whereas RERM does not. So there's like some separation between what SGD can do and RERM can capture. And yeah, that's the insight.
Okay, thank you.
Right. So the takeaway is like using through this negative result, we show that success of SGD for SEO cannot be captured through implicit regularization. Any questions?
I guess this really challenges conventional wisdom about the problem, right? Like most people, or a large amount of people think the opposite, right?
Right. Yeah. So this like this negative result we think is interesting because prior to this negative result, there was a huge momentum in the community in trying to explicitly find the regularization functions that capture the performance of SGD. And now it seems like maybe like for problems of interest, it's still true, but we cannot be certain that it always happens.
Can I ask a question?
Yes.
Just to digest this result, if I take the regularizer to be 0,
right.
What does this result say?
So this result says that ERM fails for SEO problems, which is the, okay, so let me go back to what I meant by regularization. So if you plug in the R to be 0, this is just showing that the solution that minimizes the training loss, first of all, will not work, and second is not equivalent to what SGD would return.
So what do you mean by it doesn't work? It doesn't solve the generalization problem, or it doesn't solve the training problem?
It does not solve the generalization problem. So our result shows that for any regularizer, in particular for ERM, when we set R to be 0, there exists a SEO problem for which that solution will be omega-1 suboptimal.
Okay, so F here is the expectation with respect to the underlying distribution. It's not the training loss.
It's not the training loss.
Okay.
Yeah, so it's basically, again, I mean, it's basically the no free lunch theorem, but you can show that the counterexample is a convex problem rather than arbitrary counterexample in the usual no free lunch.
Exactly.
Right?
Exactly. Right. So just to clarify, throughout this talk, we only care about performance with respect to test loss. So all the results that I will state will be in terms of test loss performance. Okay, so the key insight to show this negative result is to consider SEO problems for which the test loss is convex, but the loss for every data sample may not be convex. But the distributions are such that when you take expectation, it leads to a convex test loss. I'll come back to the exact constructions in some time, but let me first compare this observation with prior work for SEO. So one of the most closely related works is this paper called SEO, Stochastic Convex Optimization by Shale Schwartz et al. In 2009. In this work, they considered SEO problem where even the instance loss on every data sample is convex in W. And once you have that property, they show that RERM with L2 regularization matches the performance of SGD. In our setting, each data loss may not be convex. And this shows a stronger separation in terms of SGD and RERM performance. There's also been some recent work that shows difference between the points that are reached by SGD and RERM. In particular, they show that the solutions that are returned by SGD are qualitatively different from the solutions that are returned by RERM. So it's not the case that SGD is going towards an RERM solution. However, the gap between the two solutions in terms of their performance guarantees could be arbitrarily small in their constructions. We provide a stronger separation where SGD performs at a rate of 1 by root n, but RERM fails to beat a constant suboptimality guarantee. Okay, so now I'll go into the proof of this result. I'll first show the proof for L2 regularization and then discuss how to generalize it for other regularizer. As I said, the key idea is to construct SCO problems for which the loss for every data sample is not convex. In particular, the problem instance that we consider is highly over-parameterized. The dimensionality of the problem is exponential in the number of samples. And for now, like this is for presentation, but in the paper, we also discuss how to make it polynomial. So you should not be too much worried about this exponential dependence. And each data sample, Z, has two parts, X and Y, where X is a binary vector in D dimensions, and Y is either -1 and +1. The instance loss that we construct is as follows. It's Y times the norm of coordinate-wise product between two vectors. So this dot O notation is a coordinate-wise product notation, where the two vectors I take, the first one is W minus E1, and the second one is just the X vector. Okay. And the data distribution is such that the samples X and Y are drawn where X is uniform over the hypercube. So every bit of X is either 0 or 1 with equal probability. And Y is +1 with probability 3/4 and -1 with probability 1/4. And X and Y are independent of each other for every sample. Okay. So now for this construction, it should be easy to see why SGD works. In particular, if you look at the test loss, because Y is independent of X, you can just decompose it as, you can separate the +1 and -1 components, and once you plug in the relative probabilities, you get a positive value of half over there, which is a convex function, which is minimized at E1. Furthermore, you can also show that it's Lipschitz, it's a norm function, the gradient is always bounded by 1, and the variance is also bounded. And thus, using a previously discussed result, we can argue that SGD for this problem finds a 1/square root and suboptimal solution. Now, let's see what happens for RERM for this problem. In particular, the RERM algorithm returns a point that minimizes the trailing loss with this loss function, and plus a regularizer, which in this case would be lambda norm W square. Now, what happens is, because the dimensionality is so high, for any data set S that you sample, you will have the following interesting phenomena with a constant probability. That is, there exists some special coordinate J hat, such that for all the samples in your data set for which the label is 1, this coordinate would take the value of 0. And for all the samples in your data set for which Y is -1, this coordinate takes the value of 1. And the existence of this coordinate is fundamental to show why RERM fails. Furthermore, you can argue that since Y is +1 and -1 with constant probabilities, the share of data for which Y is -1 would be at least n/4 up to concentration. Okay. So now let's see what happens to the RERM algorithm, regularized empirical loss in the direction of J hat. So this is a slightly technical slide, so I'll go over it slowly. So suppose you try to evaluate, suppose we are evaluating the regularized empirical loss in the special direction J hat, which exists for your data set with constant probability. What happens is, you can divide the empirical loss into two parts. The first part that contains all the samples where Y is +1, and the second part contains all the samples where Y is -1. But recall that J hat is such that whenever Y is +1, the value of X J hat is 0. Okay, so the second term vanishes. This is equal to 0. Furthermore, J hat is such that whenever Y is -1, the X for that J hat is always 1. So you get a linear negative term over here. And this is the key to the lower bound. In particular, when you're looking at the empirical losses with constant probability, you have these directions where the empirical loss decreases the further you move away from zero. And this leads to a trade-off in terms of like how high or how large, or how large or how small you should set the value of lambda. If you set lambda to be super small, this negative linear term will make you drift far away from the minimizer. And if you set it to be super large, it will push it towards zero, which would again be far away from the minimizer E1. And we can argue that because of this negative direction, there's no value of lambda which actually returns a good solution, which suggests that RERM fails. And to extend this proof for general regularizers, it's almost the same function, but instead of having a E1 in the construction, we choose some other vector that depends on the regularization function R. So the problem we construct is dependent on the regularization function. And again, the proof follows by showing the special coordinates along which the empirical loss decreases and creates this tension.
So the only thing you have to take is the alpha to handle general.
Yes. Like the choice of alpha is a bit tricky, but yeah, that's the only difference. All right. So to summarize this section, we show that for any regularizer, RERM fails. There exists a SCO problem for which RERM fails. And this is a sad story for implicit regularization because this suggests that even for the simple problem of SCO, SGD cannot explain, the success of SGD cannot be explained through implicit regularization.
I have a question. Maybe it's very slightly stupid, but this reminds me of coercive functions where the farther you move away, if the data are separable, then the farther you move away from the the larger the size of the parameters, then the smaller the loss. So if you add a regularizer, then you're basically constraining the weights, so you will never actually get a zero loss. But both the regularized classifier and the unregularized classifier, they both find the correct signs for the classification problem. So in terms of classification, both the SGD solution and the regularized solution will be actually accurate.
Mm-hmm.
Is it the same here? Like, okay, the loss might not be the same, but in terms of classification, you might actually be solving the problem.
So this is not a classification problem, it's just an optimization problem here. And
yes, but the y's are plus minus 1, right? So is another classification? Y's are the labels, is that right? Am I missing something?
So you can think of y's as labels, but the loss function is not like a classification loss function.
Yeah, right. But here's the thing. Here's the question: is the regularized solution and the SGD solution, do they both find the correct signs for the labels? Because if I use, let's say, some indicator function as the loss function, they both are going to be accurate.
Right.
So I'm not sure how the importance of the gap in the losses. It seems that the prediction accuracy is more important. And again, this reminds me again of coercive functions. Coercive functions are functions where you can just it's like e to the x, right? The more negative x is, the smaller the loss is going to be.
Mm-hmm.
And yeah, you put a regularizer on this, you will never get a zero loss. But the question is, do you find the correct sign? Yeah, that's.
I do not know the answer whether you find the correct signs or not. That's a
okay.
That's a good question to.
Okay.
Yeah. I'll come back to that question when I will be discussing neural networks, and over there we explicitly look at classification losses. So we can discuss the implications of this question over there.
Okay, sure, thanks.
Yeah. Cool.
The negative instance that you come up with, how contrived is that negative instance? How is it likely to occur in quote unquote real life?
So yeah, so the question is how contrived is a negative instance? I think it's fairly contrived. It's like I'll come back to some other like simpler and more practical negative instances when I will be discussing deep learning setting. But the results there are not as clean as a separation that we show for this contrived example.
Is it somewhat similar to the Nagaraj-Coulter example?
No. So we show negative results for simple two-layer linear neural networks. But the results are not in terms of, I'll come to that, like, yeah. So what can happen is this example can be embedded into a neural network, but it's a very contrived embedding. So like it's like yeah. On the other hand, like this insight that you can have these functions which are like +1 and like positive and negative signings, and they add up to lead to a global positive sign. This I feel can happen in many practical settings, especially once you like stack up linear layers. The weights can be positive and negative, but they add up to being something positive. Yeah. Okay. So that was all about implicit regularization. So now I'll move on to the role of batch size. Recall that SGD algorithm is a small batch size method where you use one sample at a time. To make things more concrete, you take a pass over the data set, and for every iteration, you use 1 point from the data set. And we discussed that this works for SEO problems and it's optimal. On the other extreme, you have large batch size methods, which just use all the data points for every update. So this large batch size method, GD algorithm, takes t steps of updates, and for every step, use the entire training sample to compute a gradient. And the question we are interested in is how well does GD compared to GD perform for SEO problems, or like how well does large batch size perform as comparison to small batch size methods? So in particular, one thing to note is if I let GD to convergence, the final iterate will be the minimizer of the training loss, because all I'm doing is doing a gradient descent over the training loss. It can get stuck in weird solutions like if there's Fourier stationary points, but the hope is it will go to a minimizer of the training loss. And as we discussed before, there are SEO problems for which ERM fails. This is the case when regularization is 0. So we do understand that there are SEO problems where if you run this large batch method till convergence, it will fail to perform as well. But what about early stopping, or what about like other batch size, other step sizes, etc.? So the question really is like for SEO problems, can GD match the performance guarantee of SGD? Can this large batch size method match the performance guarantee of SGD? And so far, I've been a bit vague on what I mean by GD matching SGD. So there could be 3 kinds of comparisons I can be doing. The first comparison I can do is in terms of work or total number of gradient computations that I need between the 2 algorithms. This is like essentially a running time comparison. And this has been well studied like almost a decade ago. And the observation is that since SGD uses only 1 sample at a time, it requires 1 gradient computation for every iteration and does n iterations to find the optimal solution. Whereas every single step of GD requires to compute the gradient all the training samples. So by the time you compute one gradient descent update, GD update, SGD has almost converged to the optimizer. So SGD is better when you compare in terms of running time. The second comparison, which is more motivated from modern applications, is in terms of number of iterations, which is like if I run the two algorithms, how many iterations does GD require to find a similar solution as compared to SGD? This has been recently studied by a few works where they showed that after n solutions, the performance guarantee of GD is something like 1 by 10 to the 1 by 4. And this suggests that GD requires quadratically more number of steps as compared to SGD to reach a point with a similar performance guarantee. However, the real separation that I think, like as learning theorists I'm interested in is in terms of sample complexity. Is it the case that GD requires more samples or less samples in order to find the same solution of the test loss? And this has not been looked at before in any of the works that I'm aware of. So we show in this work that there exist SCO problems for which no matter what step size you use for GD, no matter how many time steps you run GD for, the final solution will have a lower bound of 1 by 10 to the 5 by 12.
But could there be problems in which the inequality is in which because it just exists a problem on which GD is not working well, but maybe there's another case in which it's the other way around.
Yeah. So this is a worst case comparison between the two algorithms. Because
but worst case could also go the other way around. I mean, the same time, it's not contradictory.
So for any SCO problem, SGD has 1 by root n rate. On the other hand, in the class of SCO problems, there exists a problem where SGD has a 1 by 10 to the 5 by 12 lower bound. So this is a worst case comparison over the set of SCO problems.
Okay, so it's the difference between n to the 6 over 12 to n over 5 over 12.
Exactly.
Okay.
I guess it's possible that it could be a bigger separation.
Yeah, this is not the tightest possible lower bound. But to the best of our knowledge, this is the first statistical separation between SGD and GD. Here we show it for SCO problems. Shai, I can come back later to the separations in the general learning setting. I do have some comments on that as well. Okay, so this statistical separation between GD and SGD is shown using the constructions from prior work that provide separations in terms of iteration complexity. So the prior work that discusses this iteration complexity separation provides the following result. They construct a SCO problem for which GD needs to be run for quadratically more number of steps, in particular n square steps, so as to match the performance guarantee of SGD. But at the same time, they also show that if you, for this problem, if you want to match the performance of SGD, GD has to be run with a smaller step size, in particular with a step size of 1 by n to the 3 by 2, instead of 1 by root n. And this just sets the stage for how we can show a statistical separation. In particular, we consider another SCO problem where we argue that when you run any algorithm with a small step size, it crashes. So large step size is fine, but a small step size fails to find the optimal solution. And if you just combine the two constructions, like their SCO problem and our SCO problem, you get a SCO problem for which no step size works. In particular, if you consider a large step size, then their problem fails because they require a small step size to match the SGD performance. And if you consider a small step size, then our construction fails where we explicitly require the step size to be large. And this together suggests that GD fails for all step sizes for this problem.
Sorry, can you say again what the result is? Was like it said GD does well.
Yeah, so it says GD does well, but in order to match the performance of SGD, first of all, it needs to take more number of steps, in particular n squared steps. Second, it requires a smaller step size. And the smaller step size is what we are pivoting lower bound on. Okay. Right. So let me just quickly describe what this construction is that does not allow a small step size to work, but allows a large step size to work. It's through this complicated plot. So let me go over it slowly. So the population loss is a nice ReLU-like function. So it's a ramp basically. It's the one denoted by dotted blue lines in between. So it's a line and then flat. So the test loss is a nice convex function. But on samples, there are these little kinks. These kinks are actually very fine in terms of their width is like super small. For scale, I've made them large. But when you collect samples on empirical, the instance loss FWZ has these kinks which balance off each other at the population loss. So either you have a green kink like this or a red kink, and both of them happen with equal probability. So they vanish at the level of test loss. But when you collect a data set and look at the training loss induced on this data set, it will have many of these kinks here and there. And these kinks are what stop a small batch size algorithm to proceed because they're almost flat for half of their width. So if you use a very small step size procedure, it will get stuck in one of these kinks, but a large step size will just jump over it. Okay, so x-axis is the value of the parameter, and y-axis is the loss value. Yeah. So here, think of like this as a GD update where the parameter is slowly increasing, and this is a SGD update or a GD update with very large step size where the parameter is quickly increasing. And the insight is when you look at the training loss, it has a lot of these kinks. So if the parameter is slowly like taking little steps, it will get stuck in one of these flat regions where the gradient is 0, and then it's stuck. But if you use a large step size, it will jump over all these kinks with constant probability. Okay, so takeaway: small batch size SGD works better than large batch size SGD for SEO problems. Okay, now I'll quickly discuss the role of multiple passes. So the multi-pass SGD algorithm is as follows. You take k passes over the data set. In each of the pass, use one sample at a time, and in the end, return the final solution over the last pass. And in terms of data usage, it does reuse the data multiple times, right? Like it does k passes over the data set. But it's not the similar reuse of data as is done by GD algorithm. And this also works very well in practice. So the first thing to observe is this multi-pass algorithm can be matched to compete with a single-pass SGD algorithm. In particular, a standard trick of cross-validation implies that you can guarantee that whatever solution the multi-pass algorithm returns is at least as good as an SGD solution. In our work, we show that there are SEO problems for which the multi-pass algorithm can return much better solutions as compared to a single-pass algorithm. But there are SEO problems for which if you run only one pass of SGD, no matter what step size you use, you're always lower bounded by 1 by root n. If you use k passes of SGD with a particular choice of step size, you get a nicer convergence of 1 by square root kn. But if you decided I'll just use all the data points at the same time and compute RERM, then you have a lower bound of constant.
Are all these
Yeah. So all of these three results hold simultaneously for the same SCO problem. And the takeaway from this is just like multi-pass SGD with validation is at least as good as single-pass SGD, but it can be much better in many cases.
Just going back to your empirical finding that at the beginning, not your empirical finding, but the empirical finding. The first two results were contrary to that. Well, this is kind of more in line with it. Is that right?
So the empirical findings were SGD works. The second was large batch size is bad as compared to small batch size, which is what we discussed using statistical complexity, sample complexity separation. And the last one was that multiple passes help. And yeah.
Sorry, I have one more question. Maybe I'm misunderstanding. The way you define SGD isn't really randomizable order. It's just stepping over the whole data set. And if you do multiple passes, it uses the same order.
Yeah.
Whereas in practice, I think SGD typically involves randomizing the order of the data set.
Right.
Does this change if you do that?
So if you just do one pass and you assume all the samples were sampled IID, it's equivalent.
Yeah.
Whether you
multiple passes.
It does. Yeah. So the multi-pass algorithm we consider here goes through samples in the same permutation.
Right. Does it help or hurt?
For this lower bound, it doesn't matter.
Okay.
Yeah. I can quickly discuss what's the key insight for why this benefit of where this benefit of multiple passes comes from. In particular, we consider SCO problems where taking a second pass over the dataset reveals you some fresh aspects of data which are not visible in the first pass. So a pictorial representation is here. Sorry for the poor quality. But so the SCO problem consists of two variables, W and W bar. And the value of W bar decides which of the instance losses of W you see. In particular, like here's a mathematical way of representing this. So when W bar is less than 1, you get samples from WZ1. And when W bar is greater than 1, you get samples from WZ2. And the losses are such that when you start optimizing, W bar always increases. So what happens is after you're done with your first pass, the value of W bar increases and you switch from getting samples from WZ1 to getting samples from WZ2. But Z1 and Z2 are such that they are from the same distribution. And if you look at the test loss, it doesn't know whether, like, it doesn't distinguish between Z1 and Z2. So the second pass is essentially giving you IID samples from the same distribution, which help in like improving the rate of conversion in this case.
Is Z1 and Z2 the same thing?
So
the same data set?
Yeah, so every data set has every data point has two parts, so Z1 and Z2.
Oh, every data point. Okay.
And in the first pass, you only get to see the Z1 part. And in the second pass, you get to see only the Z2 part.
What does it mean in terms of the semantic meaning of a data set? Like what is Z1 and Z2?
Yeah. So think of like every image as like not in terms of image, but like you can think of it as second pass, like revealing you some parts of data which are representative of the distribution, but not really like.
Why are there only two parts? There could be more than two.
Yeah. So that's
one more pass. You could see more number of these.
Exactly. So for K passes, we have a construction that uses K of these.
I see.
Yeah. So this is only for a 2-pass proof.
Yeah.
Cool.
So like, what is the dimensionality of like one data point? Is it like a
Yeah.
Okay. Do you think this could be like we're looking at this one data point, and we're looking at k forms of this particular data point, right?
Right.
How about we look at this point k times,
Yeah.
but not from making passes, but by adding different layers, or I don't know, what I mean is, what I get from the slide is basically that a data point has different kind of forms.
Yeah, yeah.
And these kind of forms can be looked at. Do you think it can be looked at by making passes, or can it be we can look at all these forms by making layers, or different convoluted views on the data set?
So here I've simplified the construction a bit, but in the actual construction, you can only look at this by taking different passes.
Okay.
Right. Like that's why there's no way if you take like larger steps in the first pass, like SGD has a lower bound, one pass SGD has a lower bound of 1 by root n for this problem. But again, this is a very contrived example. It's like, yeah. So this is just an example to show a problem where multi-pass SGD is provably better than a single pass SGD. Yeah. So I'll quickly go over beyond SCO setting. So in particular, like so far, I've been discussing these various properties of SGD for stochastic convex optimization problems, but we know that test loss for deep neural networks is not convex in W, right? Like, however, like in many empirical as well as theoretical works, there have been other properties that have popped up. For example, star convexity with respect to the optima minimizer point, or convexity along the path taken by SGD, or this thing called linearizability, all of which also guarantee that SGD performs for these problems. In particular, the linearizable loss is as follows. It just says that suboptimality can be upper bounded by a constant times this product between gradient and W minus W star. And if you recall the proof for SGD, this property implies that SGD also works for linearizable losses with an extra constant C. So the question is, okay, like there are some other properties under which capture some sort of like deep learning models. And these properties also imply that SGD works for these problems. So can we show some separations in the spirit of what we showed earlier for some deep learning settings? So we consider two-layer diagonal neural networks. So these are problems where the first layer is not fully connected, but every input node corresponds to one hidden node. So it's like both the layers are sparse. And if you consider various losses here, like absolute loss or linear loss or hinge loss, which corresponds to classification losses over the data set, you can show that these two-layer diagonal neural networks are linearizable for many data distributions. And thus SGD performs for these problems, but at the same time, you can show that ERM fails to find a good solution. And if you move beyond two-layer, like multi-layer neural networks, linear neural networks, we can also show linearizability. And we can extend the failure of ERM to LP norm regularizers, so any PF norm regularizer. But in general, we don't have a strict separation in terms of RERM versus SGD in neural network setting right now. So it would be interesting to figure that out, and maybe like going towards fully connected neural networks can lead to such separations. Okay, so I'll quickly summarize. So we discussed the role of implicit regularization for SGD. In particular, even for SCO problems and some deep learning problems, implicit regularization cannot explain the success of SGD. Then we looked at small batch size versus large batch size and showed a statistical separation between SGD with small batch size and SGD with large batch size. And finally, we considered a multi-pass SGD algorithm, which is at least as good as single pass SGD, but can be much better than single pass SGD for some problems. And finally, like this idea of linearizability that I discussed towards the end, which captures neural networks, is also not sufficient because we know there are many deep learning settings which are not linearizable, but SGD works in practice for these problems. And so the question which I'm very interested in for future work is what other properties of this test loss imply that SGD succeeds to minimize this test loss. In fact, like the reason we even started to look at SGD for these practical problems is because we have this implicit assumption in our head that maybe the loss landscape is very nice. And if you had the access to test loss and you directly run gradient descent on the test loss, it would have gone to a minimizer. So one question to ask is, suppose I give you this as a property that your test loss is very nice and running gradient descent takes you to the minimizer. Does that imply that even SGD takes you to the minimizer? Great. And finally, like, how do we improve our SGD? Great. Thank you. Questions?
Right, yeah. We can take questions.
Yeah.
Can you say that on the thing as well?
Yeah. We can take questions now.
It's more like a clarification question. So in the multi-pass section, you mentioned that, say, we are taking 2 passes over the data. So is the first pass just looking at like half of the features of the data, and the second pass is looking at the next half features of the data?
Exactly.
That's how it is.
Yep.
Cool. So in K passes, you divide the data vector into like K segments, and then.
Yep.
I see. Okay. Yeah, okay. Cool.
Yeah. And I guess like another takeaway from that example is that which part of the data you see depends on a third variable, which is W bar. Yeah. And you need to train W bar to make its value larger than 1, or like do some sort of like optimization in the first round, and only then you are able to see the second part. Yeah. Like it would be super interesting to construct simple like linear regression problems where you can truly show multiple passes help. But these are not like, these are very contrived SEO problems.
Could you speak about adaptive optimizers and maybe using the volume spectrum?
Right.
Learning data.
Yeah. So the first result is for RERM, where there's no scope of adaptivity except for the scaling parameter. The other one was for small batch size versus large batch size. And over there, I was feeling like adaptivity can break through the lower bound. In particular, lower bound relies on having these flat regions, which are adapted to having a fixed step size that gets stuck on them. So I feel like if you do some simple tricks like take a random big perturbation, if you're ever stuck, and then see what happens, these kinds of algorithms can escape these kinks. And for the last one, in terms of multi-pass versus single pass, our upper bounds and lower bounds are for like, our upper bounds are for like a fixed schedule of step sizes. So there's a scope that maybe if you use like other step size schedules, you can construct simpler problems. Yeah.
Do you think this should change like how practitioners think about machine learning still, or how theorists should think about machine learning, or both?
I think our target is theoreticians rather than practitioners, because like most of the, like so far there's no new insight that was not like observed before. I think the empirical observations that started with are like well established in a practitioner side. Yeah.
Right. So you want maybe theoreticians to question their assumptions.
Yeah, so that's the first part. Like you need to be very careful as to like, even in the SEO problems, like there are two worlds. First is you only assume the test loss is convex and some variance bound and so on. And the second world is you assume even the instance loss is convex. And the story is very different in the two worlds.
Have any other previous work looked into this distinction about like instance loss versus the population loss being convex?
Yeah, so it's very interesting. Like most of the, so this is my limited knowledge, so Shai can correct me if I'm wrong. But I feel like earlier to like a lot of machine learning, like Nemirovsky and Newton explicitly looked at problems which are convex at test loss, and there's no guarantee for like individual data losses. And However, like most of the learning theory papers are concerned with problems where even the loss function on every data sample is convex, right? But OR and like classical optimization people only have a test loss convexity assumption. Right, and in terms of like practical applications, I think like this question I feel might have some impact as to maybe it can lead to some other insights as to how you can modify SGD to work whenever gradient descent on the test loss works.
I'm just curious. So when we make these assumptions about the test law set that we, for example, look at linearizability, this sort of implicitly restricts the set of distributions that we're allowed to consider and what are the guarantees give, right?
Right.
So we can't give some like arbitrary factor guarantee for any distribution. It has to be for distributions such that the resulting test loss is linearizable, for example.
So in the paper, we do discuss extensions to general learning setting. So what you are pointing out is, it's like if you consider any possible distribution over the data, still the problem should be learnable.
Yeah.
And over there also, we can show some separations. In particular, we construct a instance of general learning setting, where for any distribution, you have a 1/n to the 1/5 rate. Okay, but if the distribution is such that the test loss is convex, you get a 1/√n rate. However, this rate can only be achieved by SGD. So in the worst case sense, SGD is like similar to like other algorithms, but over this subset of distributions, it's superior to like RERM. Yeah, but there could be other subsets where RERM is superior. Yeah. So yeah.
Any other questions? Well, thanks, guys, again. Great talk.
Thank you. Cool.